We are looking at a paper today called Fixed Point Reasoners, Stable and Adaptive Deep Looped Transformers. This is new work from researchers at the Ellis Institute, Max Planck, ETH Zurich, and Liquid AI.
Yeah, it is a really, really fascinating one.
Right, and for everyone out there building reasoning models, here is your high-energy 60-second download straight up. So the entire field is trying to scale test time compute. Right?
Basically trying to get models to spend more time thinking on the harder problems.
Exactly. And a lot of folks are exploring loop transformers as an alternative to chain of thought, mostly because loops scale depth rather than sequence length. But looped models hit two massive walls,
which are notoriously hard to get past.
Yeah, first is the halting problem. Like, how does the model know when to stop? Most rely on adaptive computation time, or ACT heads, which are incredibly finicky to train.
Oh, a total nightmare.
And second is signal propagation. To keep the deep loop from exploding, older models use post-norm, which just totally degrades the main signal.
Right, the gradients just vanish.
So this paper introduces the fixed point reasoning model, or FPRM. It throws out the ACT head entirely. Instead, it lets the model loop until its hidden state converges to a fixed point.
It uses the convergence itself as the halting signal.
Exactly. And to fix the signal degradation, it switches to pre-norm, paired with learnable residual scaling parameters.
Which is such a simple but powerful fix.
Yeah, the result is a single loop, 7 million parameter architecture that naturally scales its compute based on difficulty. It absolutely demolishes complex 27 million parameter models on extreme Sudoku, ARC-AGI, and intense state tracking benchmarks. Welcome to AI Paper Slop, the YouTube series where we break down the AI research that actually matters.
I mean, it really is a massive structural paradigm shift for how we approach latent reasoning. To appreciate the gravity of this, we kind of need to look at the current obsession with chain of thought.
Right, because everyone is just doing IT right now.
Yeah, everyone. But chain of thought scales compute along the sequence dimension. You force the model to verbalize its intermediate steps, literally outputting tokens just to think.
Which eats up your context window immediately.
Exactly. It bloats your KV cache and requires these highly specialized training regimes with heavily handcrafted reasoning traces, but looped architectures bypass that entirely. They scale along the depth dimension.
By just reusing the same weights over and over.
Yeah, you take a single block of weights and apply it recursively in the latent space. That recursive application is just a brilliant natural inductive bias for algorithmic tasks. Because, an algorithm is essentially the same operation applied repeatedly until some condition is met.
Right. But the baseline approach to building these looped models has been severely flawed. I am looking at models like TRM, the tiny reasoning model, or HRM, the hierarchical reasoning model.
Yeah, the heavy hitters from last year.
Exactly. And they try to achieve this variable test time compute by using ACT modules, adaptive computation time. Okay, let's unpack this. Why does ACT fail so spectacularly in practice?
It's a mess.
I read the discrete optimization issues in the paper, but what does that actually mean for the training dynamics? It feels like hiring a separate manager just to watch a worker and guess when they're done.
That is a great analogy, yeah. Think about the fundamental nature of neural networks. They run on smooth gradients, right? They need continuous landscapes to back-propagate errors.
Because without a smooth slope, the math just breaks.
Exactly. ACT introduces a discrete stop-or-go decision at every single iteration. It is like trying to train a self-driving car, but the steering wheel only has two positions, hard left or hard right.
Oh, wow. So it's a completely non-differentiable nightmare.
Completely. The model has to learn to output a halting probability, and you have to force a continuous relaxation of that discrete objective just to get the gradients to flow at all.
So you're just tricking the math.
Pretty much. The optimization landscape becomes notoriously brutal and heavily dependent on hyperparameter tuning, which creates a massive disconnect between the model doing the actual logic and the mechanism telling it to stop.
And that disconnect becomes painfully obvious in out-of-distribution tasks, doesn't it?
Oh, painfully. The paper highlights this beautifully with the A5 and S5 state tracking tasks. These are rigorous tasks based on permutation composition.
Right, the alternating group on 5 elements for A5 and the full symmetric group for S5.
Yeah, basically the model has to track a complex mathematical state through a long sequence of updates. So when they tested the baseline TRM equipped with an ACT head on sequence lengths of 128.
Which is way outside its training distribution of length 32, I should add.
Right, exactly. It completely collapsed. It scored barely 45.8% on A5. The ACT mechanism either totally exhausted the maximum compute budget without solving the problem, or it just failed to adapt at all and stopped way too early.
It fundamentally lost the plot, which makes the FPRM approach so elegant.
It really is.
Instead of trying to force a non-differentiable halt module on top of the network, you just let the network keep processing the state until the state stops changing.
Yeah, once the hidden state converges to a mathematical fixed point, you're done.
Right, meaning the output of the loop is essentially identical to the input of that loop, so you just halt. But this brings up a huge physical reality. If we fix the halting, we still have to survive the loop itself.
Yeah, the curse of depth.
Exactly. When you unroll a looped architecture dynamically, you might be unrolling 50, 100, or 200 iterations. It turns into a massively deep network.
Which brings a whole new set of problems.
Right, and in standard deep transformers, we all use prenorm to keep gradients flowing smoothly and prevent rank collapse. Why on earth were these older looped baselines stubbornly using postnorm?
It comes down to a brutal architectural trade-off regarding activation bounds. In a looped model, you are passing the exact same representation back through the exact same set of weights over and over again.
Right, it's a literal feedback loop.
Yeah, so if your activations aren't strictly bounded, your hidden states will exponentially blow up to infinity as the loop iterates.
They just scale to the moon.
Exactly. Postnorm applies normalization after the residual connection, which keeps those activation magnitudes strictly bounded and stops the divergence. But, as we know from incredibly deep networks, postnorm crushes the variance of the main signal.
It is exactly like putting a hard, aggressive volume limiter on a guitar amplifier.
Oh, I like that.
Postnorm is the limiter. It stops the speaker from blowing out when you crank it, but the tone gets totally compressed and muddy. The main signal gets lost in the noise as you add more pedals to the chain.
Yeah, the clarity is just gone.
Right. And prenorm takes that limiter off, giving you crystal clear dynamic tone. The residual stream stays pristine, but because it is a looped model, you are essentially feeding the guitar signal back into the pickup.
Which means instant feedback.
Exactly. Without the limiter, the loop feeds back until the amp explodes. Figure 2b in the paper literally shows this. If you take a bare prenorm looped model, the activation norms grow exponentially and fail to train at large loop counts.
That is a perfect analogy. You need the pristine signal propagation of prenorm to handle the deep reasoning paths. But you need a mechanism to prevent the feedback loop from exploding the amp.
Which leads us right to the architectural core of FPRM.
Yeah, the solution is a highly specific combination of prenorm and residual scaling, applied at two distinct levels. First, you have layer-wise residual scaling within the transformer block itself.
Okay, so breaking down the math, they introduce tied scalar parameters, alpha 1 and beta 1.
Right, for the sublayers, meaning the attention and the feed-forward networks. Alpha 1 scales the residual stream, and beta 1 scales the sublayer output.
So that is handling the flow within a single block, but then they also do iteration-wise input mixing between the loops, right?
Yes. Between consecutive loops, they use a second set of scalars, alpha 2 and beta 2. These re-inject the original input X into the new state before feeding it back into the loop.
But this isn't just an empirical hack where they throw parameters at a wall and hope it stops exploding.
Oh, definitely not. There is a rigorous theoretical guarantee backing this up. Theorems 1 and 2 in the paper lay out the math. By carefully coupling these alpha and beta parameters, the model is mathematically guaranteed to bound the iterates.
Meaning, even with prenorm, the activations will not blow up.
Exactly.
I am looking at Theorem 2 right now, and the paper makes a huge deal about the Lipschitz constant. It says that if alpha 2, the parameter controlling the recurrent state, is initialized small enough, it makes the Lipschitz constant of the mapping strictly less than 1.
Which is the magic key to all of it.
Right. But I know we are targeting ML engineers here, but let's make sure everyone visualizes this clearly. What does that Lipschitz constant physically mean for the latent space?
Think of a contractive map, which requires a Lipschitz constant of less than 1, like dropping a marble into a perfectly sloped funnel.
Okay, a funnel.
Yeah, no matter where you drop that marble along the upper edge, the slope of the funnel guarantees that with every rotation, the marble gets strictly closer to the center. The distance between any 2 points in that space shrinks after you apply the function.
Ah, I see.
Because the Lipschitz constant is mathematically constrained to be less than 1, the iterations are forced to converge to a unique fixed point at the bottom of the funnel at a linear rate.
Okay, that makes perfect sense. The mathematical structure physically prevents the loop from wandering off into infinity.
What's fascinating here is how the empirical best practices perfectly align with that strict theory. They found the absolute best performance came from initializing alpha 1 high, around 0.75, and alpha 2 low, around 0.25.
Wait, why that specific split?
Setting alpha 1 high keeps the residual stream dominant. That is the textbook fix for signal propagation, right? You just let the clear signal flow. And setting alpha 2 low ensures that strict contractive property from day one of training.
So it's building the funnel right out of the gate.
Exactly. And if you look at the distribution of these scales after training, the model dynamically widens the distribution of these values across different channels to handle complex logic, but it learns to keep the median of alpha to very small, intentionally staying highly contractive.
Okay, I buy the theory. We have a mathematically contractive model. In a perfect theoretical vacuum, it drops the marble in the funnel and seamlessly shrinks down to a fixed point.
But we don't live in a vacuum.
Right. We are working in massive, high-dimensional latent spaces, and those spaces are incredibly messy. What happens if the funnel isn't perfectly smooth?
That is where things get tricky.
Like, what if the Jacobian matrix of this function has eigenvalues that cause the hidden state to just spiral and oscillate endlessly around the target fixed point, never actually converging enough to trigger the halt threshold?
Yeah, that is a very real failure mode in dynamical systems. You can have a contractive map that theoretically approaches a point, but in practice it just bounces around the neighborhood forever.
Which would totally break the halting mechanism.
Exactly. This raises an important question. How do you force it to settle? This is why FPRM includes a specific damping mechanism, detailed in Algorithm 1.
Okay, how does that work?
Instead of jumping straight from the old state to the completely new state computed by the network, FPRM uses a damped update. It blends the old state and the new state using a step-size parameter, eta.
So it is essentially applying friction to the marble.
Well, yes, friction is a great way to look at it. If you look at the eigenvalues of the Jacobian at the fixed point, as long as the real part of those eigenvalues is strictly less than 1, damping is guaranteed to stabilize the dynamics.
And they do something clever with the decay too, right?
Yeah, they go a step further. They use a patience-based decay rate, gamma. If the L infinity norm of the residual, meaning the maximum difference across all dimensions between consecutive states, stops shrinking for a certain number of steps, the step size eta automatically shrinks.
Oh, so it physically dampens the update more aggressively to force the model to settle into the fixed point?
You got it.
Here's where it gets really interesting for the people actually trying to train these things. I am thinking about the GPU memory overhead.
Yes, the memory.
Yeah, because if a hard Sudoku puzzle requires the model to loop 100 times to reach that fixed point, standard backpropagation through time, or BPTT, would require you to unroll 100 transformer layers in GPU memory.
Which is just instantly fatal.
Right. You have to store the intermediate activations for every single one of those 100 loops just to compute the gradient. For any reasonably sized batch, that is going to melt your VRAM.
Are they just clipping the gradients, or how are they bypassing this?
They aren't clipping. They are using a brilliant mathematical workaround. This is the hidden superpower of formulating the architecture as a contractive fixed-point model.
Oh, wait, really?
Yeah. Because the system is guaranteed to converge to a fixed point, you don't actually need to backpropagate through the entire historical loop trajectory to find the gradient. You can estimate the gradient at the fixed point using a truncated Newman series.
Okay, a Newman series. Break that down for us. Well, according to the implicit function theorem, the gradient at the fixed point depends on the inverse of a specific matrix, which is the identity matrix minus the Jacobian.
But calculating the inverse of a massive Jacobian matrix is computationally impossible for large neural networks.
Exactly.
Yeah.
But here is the trick. Think of a standard infinite geometric series from algebra, like 1 divided by 1 minus x equals 1 plus x squared, and so on, as long as x is less than 1.
Right. High school algebra.
The Newman series is the matrix equivalent of that. Because the mapping is contractive, because our Lipschitz constant is less than 1, the eigenvalues of the Jacobian are small. That means the higher powers of the Jacobian quickly approach 0.
Oh, I see. So you don't need to compute the infinite series or the full inverse. You just approximate it by adding up the first few terms.
Yes, you just truncate it at a depth of k iterations. Equation 5 in the paper lays this out. This magically decouples the memory footprint of the backward pass from the number of loops the model actually took during the forward pass.
That is insane.
Whether the model took 10 loops or 10,000 loops to find the answer, the memory required to compute the gradient is fixed strictly to that truncation depth k.
That is incredible. So they get the deep reasoning without the memory explosion.
Furthermore, they train this using deep supervision over intervals of k iterations. They run the loop k times, compute the loss, use the truncated BPTT to update the weights, detach the computation graph from memory, and then just keep looping forward from that exact state.
So it is incredibly memory efficient and keeps the gradient stable throughout the entire trajectory.
Absolutely.
All right, so the theory is bulletproof. The marble finds the bottom of the funnel, the signal is flowing through the pre-norm, and the VRAM isn't overflowing. But at the end of the day, how does this actually stack up against the existing baseline models?
I mean, we are talking about highly specialized reasoning benchmarks here.
Right, the hard stuff.
It absolutely destroys the baselines. Let's look at Sudoku-Extreme, which requires incredibly deep logical search and backtracking. FPRM hits 94.2% exact sequence accuracy. To put that in context, the HRM model, which has 27 million parameters, almost 4 times the size of FPRM, only hits 55.0%.
That's not even close. What about ARC?
On the ARC-1 abstraction benchmark, which is notoriously difficult even for massive trillion-parameter LLMs trying to use chain of thought, the 7 million parameter FPRM hits 47.5%. It crushes the 7 million parameter TRM, which only gets 44.6%.
Okay, and going back to that A5 permutation state tracking task we talked about earlier, what happens there?
At the extreme out-of-distribution length of 128 updates, FPRM reaches 98.1% accuracy compared to TRM's 45.8%.
Wait, I need to jump in here because there's a massive elephant in the room that we need to address.
Yeah.
The baseline models we keep mentioning, TRM and HRM, stand for tiny reasoning model and hierarchical reasoning model. Their entire architectural claim to fame was using complex dual-level hierarchies.
Right, the fast and slow thinking structure.
Exactly. They had fast loops and slow loops. The authors of those models heavily argue that human-like hierarchy, fast intuitive thinking combined with slow deliberate thinking, was fundamentally necessary for a neural network to achieve advanced reasoning.
It was a very popular theory.
But FPRM is just a standard single-loop architecture. There is no fast loop, no slow loop, just one block looping. Why did FPRM win so decisively without the hierarchy?
This is arguably the biggest architectural revelation in the entire paper. It completely challenges the prevailing assumptions of the last few years.
Oh, so?
The authors strongly hypothesize that the complex hierarchy in models like TRM and HRM wasn't actually teaching the model to reason better. It wasn't simulating human cognition at all.
Wait, really?
Yeah, it was simply a structural band-aid compensating for the terrible signal propagation of post-norm.
Wow, so because post-norm was choking the gradients and compressing their residual stream, they had to build this convoluted multi-level hierarchy just to force the signal to reach the deeper layers.
That is the implication, yeah. By simply fixing the signal propagation at the root algorithmic level, using pre-norm and residual scaling, FPRM proves that the complex hierarchy is totally unnecessary for these tasks.
The pure single-loop architecture is vastly superior once the signal can actually flow.
If we connect this to the bigger picture, we can see this pure adaptivity in action in their Sudoku empty cells experiment. They plotted the compute used against the number of empty cells in the Sudoku grid, which is a direct proxy for the difficulty of the puzzle.
And what did that look like?
FPRM smoothly and perfectly scales its effective layers up exactly as the number of empty cells increases. It spends exactly the compute it needs to traverse the logic tree, and then halts efficiently based on the fixed point residual.
And the baselines.
Meanwhile, TRM, even when you try to force it to use ACT, either completely burns through the maximum compute budget mindlessly or flatlines entirely. FPRM behaves like a true algorithmic reasoner.
So what does this all mean for the ML engineers listening to this? The takeaway is massive.
It really redefines the scaling laws for reasoning.
Yeah, because over the last few years, the entire industry has been so obsessively focused on scaling up parameter counts, pushing toward 1 trillion parameters just to get marginally better reasoning.
Which is completely unsustainable.
Right. This paper proves that decoupling depth from parameter count via mathematically rigorous fixed-point iterations is a highly viable, massively efficient path forward.
You don't need a cluster of H100s to do deep logic.
Exactly. You can take a tiny 7 million parameter model, fix its signal propagation with pre-norm and residual scaling, let it loop until convergence without an ACT head, and it will punch infinitely above its weight class on pure logic tasks.
It really is a masterclass in treating the neural architecture and the underlying optimization landscape as a single, tightly coupled system, rather than just throwing parameters at the problem.
Yeah, it's actual engineering, not just brute force.
But There is a vital frontier this opens up. FPRM proves we can learn linear time algorithms using these loops. For every step of difficulty, it takes one more loop. But theoretically, keeping track of states optimally, like traversing a complex graph or the A5 benchmark, shouldn't require linear time.
What should it require?
In computer science, optimal search algorithms operate with logarithmic complexity.
Right, because if you are just looping linearly, your test time compute costs still scale linearly with the sequence length. If you apply this to a trillion parameter model processing massive documents, that linear scaling eventually becomes a hard physical bottleneck for deployment.
Exactly. The capability is there, but the efficiency curve still has room for a paradigm shift.
Which leaves us with a fascinating existential question for the industry. If we can build a 7 million parameter model that perfects linear time algorithmic reasoning just by finding fixed points, what happens when we push this to the absolute limit?
It's an exciting thought.
Can we find a latent reasoning architecture that organically discovers logarithmic time algorithms on its own, cutting through the search space exponentially faster while remaining Turing complete? Will these models learn to skip steps in logic the way a master chess player ignores bad branches of the decision tree?
That is the next million-dollar question.
That is a hurdle for another day. Thanks for joining us on AI Paper Slop. Keep building, and we'll see you next time.